Hello everybody, my name is Mark Anthony Taylor. This podcast is an introduction to general relativity and gives my thoughts on the theory's deficiencies. There's no mathematics in this lecture, not even a division, so anyone of almost any ability should be able to comprehend it. One of the great questions over the eons is, what is space? Space, the void between the planets, the stars? Can space be defined as a void, as what is missing? Well, there are lots of types of voids in this world. Voids of feeling, voids of responsibility, voids in the pit of the stomach when one is hungry. But these aren't the same kind of thing as one sees when one looks out at the night sky. So void isn't a very good definition for space. You can't do anything with it, you can't study the mathematics of it. But mathematicians in the recent centuries have defined space as a form of freedom, the freedom to construct paths between bodies. So when we say there is space between bodies, between objects, then we say we have the freedom to construct paths between those objects. When there's no space, when it's solid, if you want to construct a path, you have to dig a tunnel. And it's generally not easy to dig a hard tunnel. So you have less space, you have less freedom to construct a path through a solid object than you have through empty space. So the emptiness can be thought of as a maximum freedom. And when you haven't got a maximum freedom, when you've got a rock solid object, then you've got a minimum of freedom, minimum of choice. Now Einstein claimed that general relativity was the geometry of rigid bodies. Now to understand this, imagine we take something very rigid and solid like the planet Earth, and we find something as unmovable as the centre of London, and as unmovable again as the centre of Paris. So now we have 2 points on the rigid body Earth, and the Earth might move relative to the stars or the sun, it might spin on its axis, but those points don't change relative to the Earth. They are literally set in stone. So we can construct a number of bridges if you wanted to, because there's a lot of empty space above the Earth between Paris and London. In fact, we could actually even tunnel through the Earth from Paris to London. So we construct these bridges, and the bridges are made up of a number of segments, and the segments are held together rigidly with scaffolding. So we can count these segments, and if the segments are all machine-made and they're of the same part, then we can compare the length of bridges in terms of by counting these segments. So you could then look to see which bridge minimized the number of segments to go from London to Paris, and then you can say in terms of that segment, that is the shortest bridge between the 2 points. Now you could argue that defines a straight line, or you could argue whether it's a straight line. But you haven't always got the freedom to choose a straight line. You can choose what you will, given the physical limitations of your world. And you don't necessarily know what those limitations are. And you might have expectations of what they should be, but then you construct these bridges and you do the counting, and then you're surprised that one bridge is actually shorter than another. Not always the bridge you think it is. And so you have to actually do the measurement, the counting of the segments, to determine which is the smallest bridge. So the shortest distance between 2 points isn't given by intuition, it's not given by what is self-evident, but what you measure. Before general relativity, Einstein came up with special relativity. Special relativity says that space and time are part of a four-dimensional continuum, and that there's a geometrical construct which was called space-time interval, that is given by Pythagoras' theorem. We know that Pythagoras' theorem says the square on the hypotenuse is equal to the sum of the squares on the other two sides. Well, if you generalize that to four dimensions, you have the square on the hypotenuse, which is the square of the space-time interval, is equal to the sum of the squares of all the spatial components plus the square of the temporal component. So you can think of the different components between two events in space-time, and this gives rise to a four-dimensional line in space-time. And Einstein said this space-time interval was a significant object because different people, different measurement systems, while disagreeing with the amount of time and the distance between two events, would agree to the space-time interval. Special theory of relativity is not so much important for what is relative, but what is invariant, what doesn't change between two events. And what doesn't change is this space-time interval. Something sociologists all forget when they use terms such as relativism. It's the invariants that make the theory. Now, space-time is this four-dimensional structure, and it's a significant structure because of this Pythagorean metric that runs through it, these space-time intervals. And we can think of an object that is moving through time and moving through space as having a momentum through space-time. If they have their own pocket watches and check their own time flow, then we can look at their passage through what we think of as space-time using our network of clocks and rulers, and we can compare it with the time that expires on their pocket watch. So now with space-time giving us four-dimensional momentum, which Einstein shows leads to conservation of momentum in four dimensions, this led Einstein to look at the universe as a kind of fluid, and the fluid flow was through four dimensions. So whereas your average university student studying fluid dynamics studies three-dimensional fluid dynamics, Einstein was studying four-dimensional fluid dynamics. And Einstein was interested in the curvature of space-time. The curvature of space-time relates these space-time intervals and how that is related to the distribution of matter throughout the universe. Because with Einstein, he didn't assume that the bridge length between 2 points, if you like, the path length between 2 points was independent on the local matter. Einstein connected the two. And he did that with his law of gravity, called Einstein's law of gravity, which relates this fluid quantity, which he calls the energy momentum tensor. It's actually a multi-dimensional quantity, and he more or less says it's proportional to the space-time curvature. Now suppose everywhere in the universe there's no fluid, so that the energy and the momentum, the density, the pressure of the fluid is just zero everywhere at all points. Then the curvature, being proportional to those quantities, is zero at all points. And a space-time which is flat at all points is flat. So the classic solution to Einstein's law of gravity in an empty space-time is to have a flat space-time. Now you may ask the question, what happens if we introduce a lump of matter into empty space? Well, this gives rise to a contradiction, because introducing a lump of matter into a space means that there's a mass change through time. And if there's a mass change through time, then there's a mass flow. And if there's a mass flow, then there's a curvature. And if there's a curvature, it means our space-time was never flat. And this is part of the greater problem, in that the mass distribution and the curvature are not separable things. So we shouldn't say which came first, curvature or the matter distribution. They come together. Now, according to Einstein, space-time intervals aren't just an abstract mathematical concept, but they relate to length and time interval measurements. And length requires rigid bodies. You can't construct a geometry if every ruler is wobbly and deforms too easily. So you need points on a rigid body, and then you need to establish paths between those points. And then you count the number of rulers touching end to end that spans the paths, and that defines the length. That's how you empirically measure length. And there is the problem, because these clocks and these rulers, they have their own masses. The laws of geometry, Einstein's law of gravity, isn't a law of abstract geometry, but the geometry of rigid bodies. And every rigid body is made up of matter, electrons, protons and neutrons. And having matter has mass, and mass flow, and so contributes to the curvature of the space-time. But that doesn't provide a clear, consistent picture, because space-time is meant to be independent on the means of measurement. Different observers, different systems must agree on the space-time interval, although they don't necessarily agree on the components of that interval. But if the different clocks and rulers are introducing their own curvature into the system, then the measurement becomes dependent upon the measuring system. This is part of the great problem that the law of gravity isn't really consistent. It doesn't take into account the gravity of the measuring implements used in the system to form the geometry. So it's another case of measuring system not being a part of the system of dynamics itself, which is related to the same issue I brought up in my lecture, the deficiency of quantum mechanics. And there are some superstring theorists, which is a subset of quantum mechanics, who say that they can derive general relativity in terms of superstrings. Well, as I've explained, that quantum mechanics is deficient in terms of analysing or representing its own measuring system in its wave function. Measurements define or constrain the wave function, but they're not part of that wave function. They're not deducible from that wave function. Changes in measurement, changes in constraint, are certainly not contained in that wave function. So it's not surprising when we find an equivalent theory, if the superstring theorists are correct, that it suffers the same deficiency, albeit in a different kind of language. So for this reason I say that general relativity is deficient.